Actually, this is a joint work with the chairman. So what I want to do is to show you how you can deform the classical geodesic flow on the sphere stochastically. It looks not particularly hard, but I want to do it in a way preserving all the symmetries of the classical problem. Okay, a short survey of the classical problem. The Lagrangian is the important guy here, which is the free one. Here is something which is not usual. I will consider as action functional a bundle of trajectories starting from Q at the time t. And I will add a boundary condition, a final boundary condition, so that the critical point will solve, of course, Euler-Lagrange, but in addition, the momentum will be defined by the gradient of this final condition. Now consider Q point as a control. So as everybody knows, the inf of this value of action along extremal solve Hamilton-Jacobi equation. You may observe something wrong with this Hamilton-Jacobi equation. Two signs which looks a bit unusual. There are. I consider an Hamilton-Jacobi equation with a final condition, the one before. The fact is that for an Hamiltonian system, there are always two Hamilton-Jacobi equations, adjoined to each other. It was known until the 60s, and then it has been forgotten in some sense. Here is another one, which is the usual one, where it is plus the gradient of S star, which play the role of the momentum. And this one is a Cauchy problem. Now you can say, well, why the hell should I use two Hamilton-Jacobi equations for a simple system? There is a problem of compatibilities. And indeed, if you take the extremal, and if you look for differentiable trajectories, you need, of course, along these trajectories, that the two ways to compute the momentum coincide. This is a statement about the regularities, okay? So you could define as well the traditional Hamilton-Jacobi solution, S star L, with an initial condition. And then it's a different set of paths, the path ending at a point Q at the time t in the future. This is the one that we see in the textbook generally. The two guys, SL and LS star, are time reversals of each other. But it's not trivial. There is no algebraic relation between those because S star, S, and SU, namely boundary conditions, are arbitrary. In my special case, for the geodesic on the sphere, everything is explicit, and the reason why this system is interesting is because it is integrable. It is integrable because the number of first integral of the classical system is exactly the same as the dimension of the configuration space, which here is 2. Generally, we pick energy and momentum. And these allow you to integrate completely the system. Here is a stochastic deformation. First, I quantize the classical object. So there are two terms in the Hamiltonian. One term of the first order, which will represent the Brownian motion on my sphere. And this is the term that you see, the second term in the stochastic differential equation. Bi will play the role of the control. This is a velocity. And the winner on the sphere is defined like usually. Now, let me define a function which is the logarithm derivative of a solution of the backward heat equation with a final solution, a positive one. Why I do that? Because Fleming and others in the 70s have shown that SL, the solution of Hamilton-Jacobi-Bellman, as you will see, is the inf of this action functional, where there is nothing, there is no more than the kinetic term, and where the classical derivative is replaced by the drift. After all, the drift is indeed a regularization of the velocity. If you look at the guy, the integrand, you will see that indeed the geodesic drift is the logarithm derivative of the linear equation that I've written down before, the heat equation with final condition. In addition, if you compute a little bit, you will see that these integrands, when you compute explicitly, replace just the two derivatives of the angle by the corresponding logarithm derivative of the heat equation. Good. Now, as a function, SL satisfies, of course, a stochastic deformation of the classical Hamilton-Jacobi equation. There is an additional term of the second order. I need to compute second order in time derivative, so I will need also to apply the generator of the critical process to vector field. Ito had shown long ago that there are various ways to do this, and the Laplacian that I need is the one written here in terms of the Ricci. This is called often Laplace de Ram, or there is another term that I forget, dissipative Laplacian or something like that. Okay, in any case, as a result, the geodesic process, your two angles, solve a very nice equation, almost sure, unfortunately, but a very nice equation, which says essentially the acceleration is 0. This is what you want. You can check that for h bar equals 0, all what I said reduced strictly to the classical case. You also notice that the coefficient of the process, which has two dimensions here, the two angles, is completely controlled by the solution of the heat equation. Okay? Because you have this logarithm derivative. Now, here is the key observation. Defining the Hamiltonian, the energy, like in classical mechanics, so you see there are two additional terms, depending of a positive constant, h bar, and the momentum is defined like in classical mechanics. You check that if you compute the d of t of h and of p, they are 0. In other words, the two guys corresponding to the energy and momentum are martingales. Question, is it accidental? Of course, if I ask a question, this is because it's not accidental. Okay. There is a beautiful theorem of Jacobi which is deformed in the following way. This is a joint work with Christian Leonard. Take an Hamilton-Jacobi-Bellman in the Euclidean case. It's enough, but add a potential. This will be important. So the Hamilton-Jacobi-Bellman take this form, and I have a final condition, like in the classical case. Define a complete solution of Hamilton-Jacobi-Bellman exactly like in the classical case. So you imagine that you have a number of parameters in this solution, which is exactly the number of the dimension of the configuration space. You have some technical condition, and you want, of course, that for each value of this parameter, S alpha of Qt solve Hamilton-Jacobi-Bellman. The theorem is the following. You remember the equation for the geodesic case was the acceleration was 0, but this was an almost sure equation. I should not have called this an equation, this is a relation. This theorem shows you why it deserves to be called an equation. Okay, take this functional and assume that you know a complete solution of the associated Hamilton-Jacobi-Bellman. Two steps. First one, solve an implicit equation which are derivative of S alpha, the complete solution. I call the result M because each of them will be a martingale. You have made hypothesis allowing you to solve this equation. Second step, supplement Q alpha by P alpha defined as minus the gradient, the usual gradient with respect to the space. Then Q and P solve the stochastic Euler-Lagrange equation or Hamiltonian equation that I had. For example, to come back to my geodesic, there are in fact 4 non-trivial symmetries, namely martingale, in particular the one that I've computed at the beginning. So it was not accidental. It is, the idea is this is quite general. This allows you to define a notion, of stochastic integrable system. I didn't tell you how I can produce a complete solution of Hamilton-Jacobi-Bellman. But you have probably guessed that this has to do with the fact that there is a linearization of this equation in terms of heat equation. You consider the symmetry group of this heat equation. And the number of martingale will be the dimension of this symmetry group. So for example, if you perturb the free case by a V, a potential, which is at most quadratic, the dimension of the symmetry group stay the same. Your system is integrable. You have much more martingale than what you need. But of course, if you add a potential, Q4, for example, this reduces brutally the dimension of the symmetry group. You cannot integrate your system. Okay. This geodesic problem can be regarded as solution what is called the Schrödinger problem. I show you only one Hamilton-Jacobi-Bellman until now, but you can take also the time reversal. More precisely, you can consider the process which is the time reversal of the one that I've used up to now. The argument is almost the same. And Hamilton-Jacobi-Bellman turned into an adjoint Cauchy problem this time, just an additional term with respect to what was true before. You linearize as before, you get a second heat equation, adjoint to the first one. So you can wonder if there are processes satisfying all these conditions. Yes, there are. They are called Bernstein reciprocal, or free field, if you want. Those are processes who forget about older past until S, older future after U. Generally, they are, of course, not Markovian, but the Markovian have a very interesting joint probability, given here. The middle term is the integral kernel of built-in term of your Hamiltonian, and you recognize at the frontier the two boundary conditions positive of your heat equation. Take the marginal. Give me any density in the future and in the past, any. This is called Schrödinger system in the community of mass transportation. Berling in 1960, this is the one of Berling and Denis, has proved that there is a unique solution, not necessarily integrable, of this system. So my process is completely defined. It is unique. And in this sense, all the results I have mentioned, including the Jacobi theorem, all of them reduce strictly to classical statement and prove when h bar equals 0. Thank you very much.
Okay. Are there questions or comments?
Thank you very much. It was very interesting. I have, I guess, just two questions, please. The first one is, it seems to me you have a kind of, well, so to speak, stochastic deformation of Noether's theorem. So every conserved quantity of motion becomes a martingale. So is there a general theorem, or is it just a special case that you presented? How
Actually, indeed, we could not have proved this without the existence of the Noether theorem.
Right.
And you build all the martingale associated with Noether using the symmetry group of the underlying heat equation. You're right. In addition, we deform the idea of Jacobi using Noether, which it is of course what he didn't do because Noether was ulterior.
Yes.
But the idea is the same. The statement reduced strictly to the classical one at the classical limit. You're right. There is a Noether theorem behind it, a stochastic Noether theorem, and it is very general.
I see. Thank you. So if I can ask a second question. So my second question is about completeness. Sometimes you have a manifold so the geodesic flow is complete, but the heat flow is not complete. So with this stochastic deformation ideas, can we say anything about the completeness of the stochastic deformation, so to speak?
Well, the sense, the meaning of the word complete here is exactly the analog of the one used by Jacobi. This is to
no, I mean the flow extends to all time.
Yes, yes. Well, it's a good question, but notice that from the start, I've been careful to pick a compact time interval. Arbitrary, but compact, because I need boundary condition at the two. So a cheap answer is that the question, I avoid the question in this way. But you're right. It's in a close but arbitrary time interval.
All right. Thank you very much. Thank you.
Okay. Is there one more question? Or? Okay. So let's thank the speaker again.